Welcome back to Gradient Daily. Today, we are looking at infinite photorealistic worlds using procedural generation, a paper presented at CVPR 2023 by researchers from Princeton University, including Alexander Raystrick, Lahav Lipson, Zheyu Ma, and Jia Deng. Modern computer vision suffers from a severe starvation problem. To train models capable of autonomous navigation or deep scene understanding, engineers require an immense, continuous pipeline of diverse, perfectly labeled visual data. Traditionally, gathering this data meant attaching cameras to cars or robots, driving them through the real world, and paying human workers to manually draw bounding boxes and segmentation maps over every frame. As models scale up, this manual approach completely fails to keep pace. To bypass the human bottleneck, researchers historically turned to synthetic datasets. They would purchase or download large libraries of human-designed, hand-sculpted 3D assets, like trees, cars, and buildings, and arrange them into virtual scenes. But hand-sculpted assets introduce their own severe bottlenecks. A 3D artist can only model a finite number of tree variations. When neural networks train on these limited libraries, they quickly overfit to the specific geometry of those few assets. Furthermore, manually categorizing those external assets still leaves room for human annotation error. This paper introduces Infinigen, bypassing both manual collection and static asset libraries. It generates infinite, photorealistic worlds entirely from scratch. The critical constraint of the Infinigen pipeline is its zero-asset policy. It utilizes pure, randomized mathematical rules. There are no downloaded textures, no external source files, and no human-sculpted meshes involved at any stage. By relying strictly on math, the engine can compute an effectively endless combination of shapes, diverse lighting conditions, and complex structural compositions. The real-world impact of this methodology is direct. Autonomous driving systems, embodied robotics, and advanced scene understanding models can now train on visual edge cases that are too rare to capture physically. Infinigen operates as an infinite, mathematically grounded data foundry. By removing human labor from the generation loop entirely, it is designed to permanently solve the annotation bottleneck in computer vision. The standard 3D asset pipeline relies on fixed folders of static.obj files. Procedural generation completely abandons this storage-heavy method in favor of computing assets dynamically. Think of a static external dataset like a pre-painted canvas. You can move the canvas or change the room's lighting, but the brushstrokes are permanent. The underlying structure cannot adapt. By contrast, procedural generation operates like a genetic blueprint. In this split-screen visualization, we see a complex mathematical node graph on the left, acting as a recipe, which computes the specific 3D mesh of a tree on the right in real time. When you feed a new random seed into that mathematical recipe, the engine computes a completely unique asset. You get an infinite variety of trees without needing a single megabyte of hard drive space dedicated to storing static object files. In the context of this paper, these randomized mathematical rules are deterministic algorithms designed to mimic natural growth patterns and material physics. For example, to generate foliage, the system avoids copying leaves, instead utilizing fractal mathematics. An algorithm computes a base branch, recursively splits it into smaller nodes at calculated angles, and repeats the process until it forms a mathematically sound canopy. Zooming out to the macro level, the system employs Perlin noise algorithms. By layering these mathematical noise functions at various frequencies, the engine computes highly realistic terrain topologies, complete with natural ridges and valleys. Under this framework, dataset complexity is decoupled from human labor and physical storage. It becomes limited only by the amount of computational time you dedicate to running the equations. The scope of environmental coverage in Infinigen is vast. The code calculates distinct ecosystems, computing specific logic for flora, fauna, terrain, fire, clouds, rain, and snow. Creating a cohesive ecosystem requires a strict hierarchical composition pipeline. Every scene begins as an absolutely blank, flat coordinate grid. This visualization shows the start of that hierarchy. The base geometry is first deformed into mountainous terrain, using the noise matrices we discussed earlier. Once the land exists, secondary particle systems, like snow, can be introduced. Notice the procedural interaction here. the snow particles don't fall uniformly. Their path and dynamic accumulation are actively calculated based on the specific slopes and angles of the newly generated terrain underneath them. Think of these environmental elements as procedural Lego blocks stacking together to build a world. But unlike physical plastic blocks that always maintain their exact shape, the shape and behavior of an Infinigen block is calculated at runtime. Every single element adapts its structure based on the geometry of its neighbors. We can observe this complex interaction here. The tree placement algorithms actively react to the steepness of the terrain and the simulated sunlight. The density of the forest thins out over rocky cliffs and thickens in the valleys. An Infinigen scene is never a random scattering of disconnected objects. It is a mathematically interconnected system governed by reactive ecological rules. Generating a realistic environment is only the first half of the pipeline. The true value lies in extracting training data from that environment. Procedural systems contain what we call implicit ground truth knowledge. Because the code generated the world, it inherently knows the exact position, shape, and identity of everything within it. As this vertical slider wipes across the rendering, we see exactly how semantic segmentation datasets are extracted. The output is perfectly precise because the engine already knows the exact category assigned to every single generated pixel. Extracting 3D reconstruction data is just as seamless. The engine simply reads the Z-buffer depth maps directly from the rendering pipeline, providing a flawless grayscale record of how far every surface is from the camera lens. For moving objects, optical flow datasets are generated by explicitly tracking the mathematical motion vectors programmed into the engine for every frame of animation. Achieving this level of detail manually is nearly impossible. Asking human labelers to calculate exact depth values or annotate per pixel optical flow on real-world video is highly inaccurate and prohibitively slow. Infinigen essentially operates as an omniscient director. Tracking the exact trajectory of 1 million falling snowflakes is trivial when you are the mathematical engine actively generating their 3D coordinates. By leveraging the implicit knowledge of procedural systems, the cost of generating flawless, pixel-perfect ground truth labels effectively drops to zero. This comparative chart illustrates the leap in methodology. Prior synthetic dataset efforts, shown on the left, relied heavily on finite 3D asset libraries. Infinigen, on the right, relies entirely on infinite variants with zero external assets. The primary failure mode of finite asset libraries is immediate memorization. When a neural network trains on a limited set of assets, it memorizes those specific textures. As shown by the performance line here, its ability to generalize quickly plateaus. The paper's most critical finding is visible on the right. Models can learn highly robust, real-world visual features entirely from synthetic mathematical rules. The performance line scales continuously upward as the procedural's variance increases. The mechanism behind this is forced generalization. Exposing a model to infinite procedural variation removes the option of memorization. The network is forced to learn the underlying geometric and semantic features of the objects. This approach provides massive benefits during inference. When deployed into chaotic, unmapped real-world environments, they are far less likely to fail when encountering unfamiliar object shapes or lighting conditions. The visual fidelity must strictly match the mathematical variance for this to work. High photorealism ensures that synthetic textures accurately mimic how physical light interacts with rough bark, wet mud, or translucent leaves. Because the data scale is effectively limitless, researchers can now pre-train massive vision models entirely in the procedural domain before fine-tuning them on a small sample of expensive real-world data. If the procedural variance is vast enough, pure mathematical generation effectively bridges the gap between simulated training environments and physical real-world deployment. Structurally, Infinigen solves several distinct problems at once. It provides infinite data scale, ensures pixel-perfect annotation, and completely bypasses the legal complexities of copyright and asset licensing. However, replacing static assets with mathematical generation introduces a steep compute bottleneck. Calculating complex procedural geometry, volumetric clouds, and simulated light transport requires immense rendering power. Furthermore, the sim-to-real domain gap is reduced, but it persists. Even the highest fidelity synthetic data remains a mathematical approximation of physical light and material physics. Future research must move from passive vision to active testing. The next step is deploying embodied AI and robotics, like the system seen here, into physical spaces to measure precisely how well these synthetically learned features map to physical navigation tasks. There is also the challenge of environmental scope. Translating the chaotic, organic rules of nature into algorithms is difficult, but expanding this methodology to accurately compute unorganized, complex man-made and urban environments requires an entirely new set of procedural logics. Infinigen is not an exhaustive final solution. It is a foundational blueprint for fully simulated training pipelines, proving that data generation can successfully scale with raw compute power rather than human labor. This summary graphic outlines our 3 core takeaways. First, Infinigen successfully generates infinite photorealistic scenes from scratch using purely randomized mathematical rules. Second, the system requires 0 external assets, effectively solving the data diversity bottleneck that plagues static libraries. Third, by acting as the omniscient creator of the scene, the code automatically yields pixel-perfect ground truth data for complex vision tasks like optical flow and 3D reconstruction. If you found this breakdown valuable, click the like button below and subscribe to the channel. We analyze the architecture behind state-of-the-art research every single week. Check back tomorrow for our next paper deep dive on Gradient Daily.